Hi everybody, my name is Wiebke Köpp and I'm presenting our work proposing a new topology-based static visualization for temporal scalar data that we call temporal merge tree maps. This is joint work with Tino Weinkauf and we are both at KTH Stockholm. Our main objective with this work is to support the analysis of spatial temporal data, specifically scalar fields, by providing an overview. An obvious first step for that may be to just create a visualization where each time step is shown, and then creating an animation of that, or a dynamic visualization where time is mapped directly to time. We can see an example for that here. This is a scalar field that essentially represents storm activity over Europe by capturing the pressure anomaly over Europe during that time. Blue areas or dark blue areas that we can see here correspond to either strong storms or some kind of weather phenomena that is associated with a low pressure anomaly. But there is a drawback of using an animation like that. If we look at this video, then there's a couple of questions that are really difficult to answer. For example, if I were to ask you, is there any time period in here where all of Europe is covered by a low pressure anomaly? Or how long do these features that we see persist over time? Where is the longest of them? Where is the largest of them? Then we would be able to answer these questions with maybe going back and forth in the video, but a different kind of visualization could help to see that directly. And that would be a static visualization, where we can see the entire time in one image. Now, if we have only an image available, then we may use one dimension for time, and the other dimension we would need to fit all of the spatial data into. And that means that we need to take all of the data points that we have and somehow map them into one dimension. There exists methods for that. So what I've done actually here is to just go through the data in a space-filling way. This is essentially a Hilbert curve, what we're seeing here. And that creates a one-dimensional representation of our data that we can then show over time to create such a static visualization. An alternative to that is to abstract a bit more from the data and creating a feature-based visualization. So instead of mapping the individual vertices, we could extract sizes of components at different thresholds and then create a nested visualization right here where only the sizes of those are captured. Both of these are methods that have been presented and studied before. Here on the left, we have the domain linearization. For example, this one is a Hilbert curve over time computed with the implementation by Franke et al. And this here on the right is a feature-based visualization, a nested tracking graph specifically, computed with the implementation by Lukács et al. Now, both of these have advantages and disadvantages. We can certainly see some of the structure from the data in both. The domain linearization has the advantage that at every point here, over time, the spatial location remains static. So we can see how in one specific location the data changes over time. And in a feature-based visualization, we can see the individual features and may be able to estimate their length and so on. But then both also have disadvantages. For the domain linearization, here the Hilbert curve, we don't see any of the features anymore that we had in the original data. And in the feature-based visualization, we lost some information. For example, if we look at these two areas here, then we know that there is a size change, but we don't know if the transition in value is just static linear or if it's a really sharp curve, for example. So we want to combine the best of two worlds, basically, and create a new visualization that we call temporal merge tree maps that is essentially based on a feature-based domain linearization. iterating over all of the vertices in some way that retains all of the features as well. With this kind of visualization, the questions that I asked earlier are a lot simpler to answer. For example, for a time period that covers almost all of Europe with a low pressure anomaly, we can see that that happens more towards the end of the period covered. For feature length, we can estimate how long a single feature persists simply by looking at when it starts and when it stops in the time frame. But how do we get to this visualization then? Well, there are two things that we need to figure out. First off, we need to derive a mapping from our scalar field that may be in 2D or 3D to one dimension, while also retaining all of the feature and the structure that is in the data. And then things change over time, but we want our visualization to still show features in a nice, coherent way. And we address both of these through an intermediate data structure, the augmented merge tree, that captures features quite nicely in a hierarchical way, and by employing a greedy heuristic that relates the augmented merge trees over time and tries to align them in a good way. The augmented merge tree is a data structure that captures the hierarchical nature of the features in a dataset quite nicely. Its leaves are minima or maxima of the dataset, its inner nodes are the saddle points, and its root is either a maxima or a minima. All of the vertices in between are part of the connected components that are associated with those critical points. Meaning each leaf starts a new component, and then as the threshold increases, those components merge, and any vertex that is in between on the arcs of the augmented merge tree belongs to that component. And in order to create our 1D representation, we can basically reverse this algorithm to create a 1D representation that again has the exact same merge tree as our scalar field that we had originally. The way we do that is by starting at the root. Each vertex that we encounter along the way, we just sort it towards the left and to the right of our 1D space that we have available. We do that until we reach a saddle point. There, we now have to make a decision where we place it. And in order to later traverse its children, we need to make space for those children. And that point also needs to be placed in between them, such that the merging behavior in one dimension is again the same as in the original merge tree. Now you may already see that there is some flexibility in how we place those children because there's two different ways in which we can traverse them. We can either put the orange component first or last. And we'll use that later for our optimization. But let's say we place the orange subtree first. Then our saddle points gets placed in between them, leaving enough space before and after. And now we just traverse the entire tree recursively. For the first subtree, we again place any vertex that we encounter towards the left and towards the right. And for the second one, we do, again, the very same up until we have reached a saddle point that we then place in between of its children. This way, the leaf of any superarc gets placed right in between of all of its other vertices. Here in this example was a minima. If we now add back the scalar information, meaning the value of the original scalar field, then that point will again be a local minima. And you can also see, similarly, the saddle points here and here are where components would merge if we increase the threshold here. And that means we have created a 1D mapping with, again, the same merge tree. There are some intricacies with that. For example, multi-saddles cannot be accurately represented in this 1D representation simply because each point has only two neighbors. That means merging behavior of more than two components is simply not possible. But this kind of mapping essentially just splits a multi-saddle into two consecutive saddles. And that's a common way to handle multi-saddles anyways. And we could also reverse engineer again that there was a multi-saddle in the data. So that doesn't pose too much of a problem. Note that we aren't the first one to make this observation that a tree can be used to linearize data, creating a 1D representation that has the same tree as a tree in n dimensions. For example, Österling et al., Volker et al., and Clemea all created similar 1D representations like ours here as well. Now, let's look at an example of a scalar field over time and just creating our visualization, sorting each tree per time step randomly, sort of not taking temporal coherence into account at all. This data set is just a simple one where we have one Gaussian blob that remains static and another one that appears, grows stronger, and then disappears again. Not taking temporal coherence into account, the visualization would look like that. We can already see some structure in this data, but it appears as if we basically had 4 features. And the reason for that is because our trees are not aligned. If we just look at a single time step for that, then here having the large Gaussian feature and the smaller one leads to a 1D representation with, again, one larger peak and one smaller one. But in the next time step, it may be that even though in the dataset not much changed, the representation is the other way around. Now having the larger peak to the right and having the smaller one to the left. And that is the reason why we have to have an additional step ensuring temporal coherence. So how do we create temporal coherence then? Let's say we have 2 subtrees in our dataset. One where the connected components is slightly smaller here on the top, and one where it's a bit larger and has a bit of a more lengthy shape here on the bottom. And in that time step, we decide to sort them in 1D such that the smaller component is on the top and the larger component is in the bottom. Now the data changes over time, and in the next time step, our components have moved a little bit, changed their shape a little bit, and we want to figure out how to do the 1D representation such that we get a good match. We have 2 options. We can place the new larger component on top and the new smaller component on the bottom, or we can do it the other way around, placing the smaller on the top and the new larger component on the bottom. Since the sizes don't match up perfectly, there's no way we can get a perfect matching, but it's quite obvious that the second mapping is a lot better because the overlap matches a lot better to what we have in n dimension as well. We can use this observation to formulate our temporal coherence problem as an optimization problem. Essentially, we want to find a traversal order for all of our trees such that the overlap that we get in 1D between 2 time steps quite closely matches that what we had in n dimensions. If we write that out as a formula, what we get is this. We will sum over all time steps and then consider 2 consecutive time steps of that. We consider all subtrees in the first time step in comparison to all subtrees of the next time step. And our final value that we aim to minimize for each of those is the difference in overlap in ND to overlap in 1 dimension. Evaluating this equation for all possible traversal orders is impossible. So instead we go with a greedy heuristic where we keep 1 time step fixed, meaning the traversal order for that one is just assumed to be given. And from there on we go backwards and forwards in time and decide on a time step per time step basis how we should traverse the next tree such that a good match is obtained. We can do that by evaluating part of the objective locally and always choosing the better of the 2 possible orders. That means we traverse a new tree from the root And every time we encounter an inner node, we evaluate just for those two subtrees the objective for the two possible orders that we can traverse, and then look at which of the two is smaller and pick that traversal order. We do that hierarchically until we have traversed the entire tree, and then the order of that tree is the fixed order for the next time step. So how does the result look then for the dataset that we had previously with the one moving feature? Well, if we employ optimization here, then we get one feature that persists over time and one that comes in, moves a little bit closer, and moves out, which is also the behavior that we observed in 2 dimensions. But let's look at the results on a few more complex data sets. This is the result on the data set that I showed you in the very beginning. It has 281 times 181 samples in space. That is essentially a half-degree sampling of Europe. And then it covers an entire month, sampled every hour, which gives us 744 time steps. 744 is not quite enough to fill a high-resolution image in width, while 281 times 181 is too much to fill a high-resolution image in height. So we do a combination of upsampling and downsampling to fill the image nicely. In the width, we just do linear interpolation and stretch each time step a bit. And in space, we just do a subsampling, skipping some of the data points in regular intervals to fill the image. In terms of runtime, calculating this image takes about 15 seconds on 18 threads and 71 seconds on a single thread. However, the speed up comes mostly from just parallelizing over time steps when extracting the augmented merge trees. In both cases, our optimization and the assembly of the image takes about 4 seconds and cannot be sped up much by parallelizing because our optimization operates on a time step per time step basis and is thus inherently sequential. As noted before, we can now use our visualization to identify large-scale trends like this low-pressure anomaly in the end of December. And we can look at individual features. For example, the storm Anatole that we have here in the beginning of September, and compare it to some of the other important storms in that month. For example, here we have the cyclone Lothar, which in terms of size is a lot smaller, but persists over a much longer time. Then the cyclone Martin covers a bit of a larger area. And these aspects are quite nicely captured in our visualization. The temporal overview that we create with our visualization can, for example, also help us to identify distinct time periods where the behavior is really different in the data. This is an example for a cylinder dataset capturing the flow behind a square cylinder. And we can see in the visualization already that there really seem to be 3 distinct phases. And that is, of course, also captured in the original data. In the very beginning, we just have a few components right behind the cylinder. And then, over time, more components form that eventually leave the domain. And finally, we have more turbulent behavior with many components that are spread out all over space. This data set is a bit larger than what we had before, and it is also 3D, but the number of time steps is a bit lower. In terms of runtime, it takes about 99 seconds to compute this on 18 threads and about 11 minutes if we just go with a single thread. However, again, most of the time is spent in extracting the topology, and it takes about only 25 seconds in both cases to run the optimization. So what else can you expect from the paper then? Well, we show you the results on 6 different datasets. All of them have different spatial resolutions, different temporal resolutions, and some of them are 2D, some of them are 3D. We use some of these data sets to compare against existing methods, both feature-based methods as well as different domain linearizations with space-filling curves. We also study how our optimization is doing in regards to starting time steps and so on. And we study the effect of topologically simplifying our data sets previous to computing our visualization. And of course, we give you the runtimes on all of these data sets. We also have some ideas of where to take the method in the future and what to improve. And these are related to the three sources of complexity that we can have in a data set. We think that we can still be smarter in the subsampling. For the temporal dimension, we currently do a time step per time step based optimization, but it would be really interesting to look at a global view on that. Although, since the problem is still NP-hard, that may be difficult. And finally, for topological complexity, it would be really interesting to explore a temporally aware simplification of the data. Because what happens now, if you really aggressively simplify your data, it can happen that you simplify out a feature in one time step, but not in the next, giving you a temporally really incoherent visualization. So in summary, we present a new visualization method called temporal merge tree maps that are based on augmented merge trees for creating a mapping between the original scalar field dimensions to one dimension. And then using a greedy heuristic based on making local decisions in all nodes that are encountered while traversing the tree in order to get temporal coherence. If you're now interested in trying this out, then the code is available on GitHub under my name, Wiebke, at the name of the method, temporal merge tree maps. Thank you for listening.